Good to go. Good morning, everyone. Welcome to another edition of our takeaways. Today we have three speakers. We have Kyle, Ron, and Bernard, who's joining us from Cape Town. They'll be discussing the concept of building your own smartwatches, cosmic rays causing irregular errors in code, and bending a spoon with your mind. So, without further ado, I just wanted to check if anyone in the room can hear me. Anyone online? They can hear me? Just put a thumbs up if it's cool. Cool. So, Bernard, we'd like for you to share your camera and start speaking, and then we'll see if we can hear you.
Hello, everyone. Audio working?
Can everyone online hear Bernard? Cool.
Great. Well, as you can see from the title, I'll be presenting this takeaway on whether you can or should hold your own smartwatch. Now, the idea is fairly simple. I mean, who wouldn't want to do this? You could add endless possible features that would only be limited by your own skills. And while that's not technically true, we'll get back to that. You would also have complete control of your data, considering all of the personal information they capture these days, including biometrics and messages and all of that. It could also end up cheaper than an off-the-shelf solution. So the first step, of course, is to build the device. And for that, we need some kind of controller, a screen, a housing to put it in, a band to attach it to your wrist, and a battery to power it. For the controller, I went with a Waveshare ESP32, which has an integrated touchscreen, simplifying the process quite a bit. Now for the housing, I elected to 3D print housing. I have some experience with 3D modeling, so I used an awesome tool called FreeCAD and the available diagrams to design some different housings. It went through quite a few iterations. Shown here is one where it has like an external battery holder because it ended up being quite thick. Here's a quick time lapse. I had to sit there for 2 hours waiting for it to print, so you guys get to sit here for 40 seconds with me. I ended up not going with the external battery just because, yeah, probably not the best idea to have wires hanging out of it. As you can see here, you can see the final case as well as the band that I attached to it. I ended up using an existing band from a watch that I had. Then for the battery, the nice thing about the controller I went with, it has an integrated battery connector and charge controller. However, unfortunately, I wasn't able to find a battery with the correct connector. So I ended up having to solder it directly onto the contacts, which let's just say my soldering isn't the best in the world, so I will not be showing pictures of that. The next stage is to have some kind of firmware to run on it. And for that, I use a really cool library called LVGL, or Light and Versatile Graphics Library. This is specifically designed for embedded controllers like this. As you can see here, some sample code from their website where you can define buttons or other widgets with lots of different options for them. And then you can define event handlers that automatically get called. It manages a lot of the states for you, which is quite helpful. It also has a lot of features in terms of animations and tile views, so you can easily iterate and add more screens to your project. Here's just some more code. I'm not a big fan of the Arduino IDE, but fortunately you don't have to use it directly. I just use it to upload the code. Here's a quick demo of the tile view. So all of these animations and so on are built into LVGL, so I don't have to set up any of this myself. You just define what you want on a page and it'll handle the transitions and the touch controls for you. I ended up with these 4 faces, or screens rather. Of course, time, very important. It has a battery indicator, but don't pay too much attention to that because it's definitely correct. Then some basic settings, turning the Wi-Fi on and off, syncing the time, and a brightness slider. I also added functionality to connect to different Wi-Fi networks, so I didn't have to hard code a specific network I wanted to connect to. And this is all persistent throughout restarts or the battery getting flat, it'll remember the last Wi-Fi network. I also added a weather page, and I learned a bit of a lesson in reading the API docs. As you can see here, we've got minimum current and maximum temperature, as well as some other measurements. And what I didn't realize is that for the free API, this doesn't actually refer to minimum maximum for the day. Just if you're in a large city, it'll tell you, oh, the coldest part is this and the hottest part is that, but should be an average of the current, which I think is a bit misleading. Although I was very confused why they were always very similar. I did run into quite a few challenges though. The LVGL documentation, while very well set up, is quite out of date as it's constantly being iterated on. So whenever you're using their samples, you kind of have to figure out what's changed and change it accordingly. Then I ran into a lot of issues trying to implement Bluetooth low energy notification syncing from your phone, but I'll come back to that. Then unfortunately, the serial communication was not working on my unit. So while I could flash the firmware, I couldn't debug it very well and had to add like debug labels in every screen. And yeah, it was very annoying. Some hard limitations I ran into with doing this as a DIY project was the chief one, I think, is battery life. At the end of the day, you're just not going to beat a whole team with circuit board design and lots of experience with software. So I ended up with about 2 hours of battery life on average for my device, which is not ideal for a watch, but it's a cool proof of concept. The ESP32 does have some cool power states, but unfortunately, they interfered with the touchscreen functionality. So once it went to sleep, it refused to wake up, like me in the mornings. Then with the BLE notification syncing, you really need an app on your phone to send this information to your watch. And I didn't have quite the time or the available effort to do that. And while there are some generic apps available, they require pretty invasive permissions in order to function. And I just wasn't too happy about giving them those. There is a cool alternative though. I came across this app, which is called Chronos. It's developed by a man called Felix Piego, who I think is based in Kenya. And he has quite a very well set up app, as well as firmware for specifically my ESP32. That then does all the syncing, the time syncing, notifications, everything from your phone instead of using Wi-Fi. I was able to flash the firmware, get the app and everything. However, I ran into issues connecting the app with the watch, so I wasn't able to get that working. But for other people who want to do a similar project, this might be a cool way to get started if you're able to get it working. Now, something I mentioned at the start is the cost. The controller, screen, everything was about 500, which is not too bad all considering. And then 3D printing, pretty cheap. This, of course, does not include the 3D printer, which I conveniently already had. Battery is about 70 Rand, and the band I just stole, as I said, from a different watch. I think the real problem, though, is if you factor in how much time you need to spend on this. So software development, about 200 Rand an hour. 3D modeling is very similar in terms of pricing. So anytime you're spending about 30 hours on this project, you could buy a very nice smartwatch for the amount of time you're sinking into this if you were to spend that time working, which I did. I did this in my own time, don't worry. So yeah, I think at the end of the day, whether you should is really up to you why you're doing it. I think there are lots of reasons to do it, for the fun, for learning about microcontrollers and maybe some 3D printing, so even some hardware things. There's also the upfront cost is not very high. I think that this is something that a lot of people can benefit from. Some reasons not to, however, is if you don't have all the extra time in order to implement the features that you want or need from such a device. You might also want something that just works. And this is not the project for having something that works. It's a project for having something that you can show people, hey, look, I'm doing this. And when I ask you, oh, can it tell the time? You're like, sometimes. Troubleshooting can also be frustrating, especially when you're running into those documentation issues, or as in my case, when I couldn't debug properly. But at the end of the day, I think that it was a great project, and I would recommend to anybody who's interested in learning about these things that it's a great way to get started. Cool. I don't know if anybody has any questions. You might need the mic for me to hear you from this side.
Any questions in the room? Going once, going twice, online. Yeah. Thank you, Bernard.
Cool. Thank you so much, guys. Cheers.
Okay, for our second takeaway, we have Kyle presenting the irregularities of code based on cosmic rays. Thank you. So just share screen.
Can everybody hear me? Cool. In 2013, a speedrunner was playing Super Mario 64 when suddenly Mario teleported across the level, saving the speedrunner precious seconds. To this day, there has been no known explanation for this glitch, even after a $1,000 bounty was placed on whoever could replicate it. Now, the best explanation is a cosmic ray from space that struck the console's memory, flipping a single bit and altering the game's code in real time. This phenomenon, although rare, is called single event upset, or SEUs for short. It happens when high energy particles such as cosmic rays or neutrons strikes a semiconductor chip, flipping a 0 to a 1 or 1 to a 0 or vice versa. Now, this type of error doesn't cause any permanent damage. However, it can cause unpredictable behavior in computer systems, from gaming consoles to satellites. Now, you may be thinking, okay, this is just some weird gaming fluke, and why does this matter? However, SUs have caused far more serious problems. They've interfered with flight control systems, they've altered elections, they've even impacted cloud computing services. And as our technology shrinks and becomes more advanced, is making it the likelihood of SUs is increasing, making it a growing concern for engineers and researchers alike. In this talk, I'll dive into how SUs happen, the real-world consequences, and what scientists are doing to prevent them. Now we know what SUs are and how they happen. Now that we know what SUs are, let's break down the science behind them. How do SUs flip bits in your computer? At the core of this issue is something known as high-energy particle interaction. Cosmic rays, or particles traveling at nearly the speed of light, are constantly bombarding Earth. Most of these are absorbed by Earth's atmosphere. However, some make it through, creating secondary particles such as neutrons. When one of these particles strikes a semiconductor chip, it can disrupt the electrical charge stored within a memory cell, flipping a single bit from a 1 to a 0 or vice versa. Now, this seemingly tiny change can have massive consequences depending on what that bit controls. To put it simply, imagine your computer is a massive spreadsheet filled with ones and zeros. If a cosmic ray just changes one of those values, your system might miscalculate, crash, or behave unpredictably. In most cases, single event upsets go unnoticed. However, they can trigger anything from a simple glitch to a system-wide failure. So where do issues happen most often? Well, the answer depends on how much radiation exposure a system is exposed to. Space is the worst environment. Without Earth's atmosphere to protect them, satellites, space probes, and the International Space Station are constantly bombarded by cosmic radiation. NASA and SpaceX specifically designed their spacecraft with extra shielding and error correction methods to prevent from single event upsets. High altitude flights are also more at risk. Commercial airplanes fly at around 35,000 feet, where cosmic radiation is significantly stronger than at sea level. In fact, airline computers and even passengers' personal devices are more likely to experience single event upsets at cruising altitude. Now, SUs don't just happen at high altitude or in space, they can also happen at sea level. Atmospheric neutrons can also cause bit flips, especially in high density electronics such as cell towers, data centers, and even personal devices. Even your laptop and cell phone are not completely immune. With technology shrinking to the nanometer scale, modern processors and memory are becoming more vulnerable to these tiny disturbances. And as we rely more on AI, cloud computing, and autonomous systems, the need to understand and mitigate these issues is becoming all the more paramount. Now that we understand what issues are, how they happen, let's look at some real-world consequences where a single bit error has led to some serious problems. One of the most alarming incidents happened on Qantas Flight 72 in 2008. The Airbus A330, cruising at 37,000 feet, suddenly experienced a series of violent uncommanded dives, injuring passengers and crew members alike. Investigators traced the issue to the aircraft's flight control system, where a single event upset caused a faulty data reading, leading to the computer to inaccurately detect dangerous air conditions. As a result, autopilot disengaged and the plane abruptly pitched downward. Fortunately, pilots were able to regain control and safely land the plane without any casualties. However, this incident highlights how SUs can affect even highly redundant aviation systems. SUs have even affected elections. In 2003, a Belgian candidate received 4,096 extra votes due to a single bit flip in an electronic voting machine. Fortunately, officials caught the error when they noticed that the total number of votes were higher than the total registered voters. Even Google's data centers have recorded thousands of SUs. In 2009, Google researchers published a paper revealing that cosmic ray-induced bit flips were happening regularly, sometimes leading to data corruption, sometimes just to software glitches. Since then, they've implemented advanced error correction techniques to prevent this. These examples show that SUs can affect anything from a video game glitch to interfering with flight control systems. And this raises an important question. How do we protect our systems from SUs? The good news is that researchers have already come up with several techniques to prevent these. One of the most simplest and easiest is error correcting code memory, or ECC memory. Unlike regular memory, ECC memory can detect and correct single bit errors automatically. This is especially important in mission critical systems such as servers, medical devices, and even spacecraft computers. Many modern data centers implement ECC memory to prevent data corruption from cosmic rays. Another technique is triply modular redundancy. This method involves running 3 identical circuits or processes in parallel. Each one of these performs the same computation, and the system compares the results. If one of the 3 results are different, likely due to an SU, the system will ignore it and instead use a majority vote to determine the correct result. Now, this approach is often used in aerospace and military applications, where reliability is absolutely paramount. For systems operating in extreme environments, engineers use radiation-hardened electronics. These components are specifically designed to withstand high energy particle exposure. NASA and SpaceX use these kind of chips in their spacecraft to ensure that they do not suffer from single event upsets while operating beyond Earth's protective atmosphere. However, radiation-enhanced electronics are expensive and slower than commercial processes, and so they're only used when necessary. Finally, we have software-based methods, such as memory scoping. This is where software periodically scans memory for errors and corrects them before they can cause any issues. Redundancy checks, such as duplicating calculations and cross-checking data, are also common in safety-critical applications, such as finance and aviation. Even cloud providers like Google and Amazon implement software-level error correction to maintain their system integrity. These mitigation strategies ensure that SUs remain a rare inconvenience rather than major disasters. Now let's take a closer look at why this problem is becoming more important in modern computing. Today's processors and memory are built at the nanometer scale, meaning that a tiny disruption from a cosmic ray has a significantly larger impact than in older, larger circuits. To combat this, researchers are looking into machine learning and AI to predict and correct single event upsets in real time. By analyzing patterns in data corruption, AI systems can detect anomalies and correct them before they can cause any real damage. Another emerging field is radiation-aware computing. As AI, quantum computing, and autonomous systems are becoming more critical, engineers are designing software and hardware that can withstand radiation exposure. As mentioned, this is especially important in fields such as spaceflight, high-altitude flights, and medical devices such as pacemakers. While we may never fully eliminate the threat of SUs, researchers are ensuring that our technology remains reliable, even in the face of cosmic interference. Thank you. Does anybody have any questions?
There's a question in the chat. Okay.
I wanted to know how do you know that a bug in the system was because the bit flipped and not just a bug, yeah.
So that's part of the danger, is that they mimic usual software glitches and hardware errors. And so it's often quite like a trial and error process. So with things like the triple modular redundancy, if they do notice in that system that one of those are different, that's usually a good indicator that there's SEUs. Now, there's also things like parity bits and checksums that also can help detect. I know with ECC memory, if they notice in those logs that there's quite a lot of corrections, that's also a likely candidate for single event upsets. And then another thing that they often do is they do fault injections. So when they can't find any other reason why this glitch is happening, they will try and mimic what an SU would be to see if that was the cause. So it's very much a trial and error process.
Cool. Anything else from the room? Going once, going twice? Anything online? Cool. Thank you, Kyle.
Cool.
Okay. You can unmute and ask your question. With his hand. Okay, cool. Thank you, Carl. And for our last speaker of the day, we have Ron discussing the concept of bending a spoon with your mind. Thank you very much. We start.
Hello, everyone. My topic for today is bending a spoon with your mind using neurotechnology. In that regard, we'll be exploring neurotech and software innovation. So, bending a spoon with your mind is a classic magic trick that you probably either heard or seen about. It usually contains some form of showmanship coupled with a rigged spoon. But the question today is, how can we go about making it technically real with neurotechnology? Well, before we get into that, let's first define what exactly is neurotechnology. Neurotechnology is a multidisciplinary field integrating neuroscience, engineering, and computer science. It involves the development and application of technologies designed to understand, interact with, and even manipulate the nervous system. There are two main facets when considering neurotech. The first is the application of neurotech in recording and measuring brainwaves. Neurotech allows us to understand and decipher the complex workings of the brain. There exist both invasive and non-invasive methods, both with their own advantages and disadvantages. Invasive procedures enter the body through incisions or instruments, while non-invasive procedures do not break the skin. One of the most widely known tools for recording brainwaves is the electroencephalogram, or the EEG. These are probably what we're all used to seeing, a bunch of wires and nodes strapped to your head looking all cool and fancy. And to be fair, they are. These devices record the tiny electrical impulses by the firing of neurons in the brain. These are electrical signals on the magnitude of microvolts. To put that into perspective, the human body, as the conductor that it is, naturally picks up electrical noise from the environment, mostly from power lines, which is then on the magnitude of millivolts. This is already an electrical noise level of about 100 to 1,000 times. EEGs are able to filter through these while providing a meaningful representation of a person's brainwaves. Other technologies exist as well, such as the fMRI method, which produces different but similarly useful data. The other facet of neurotech involves actively interacting and manipulating brainwaves. These are usually used in highly specialized systems and in the medical field. Two well-known methods is the transcranial electrical stimulation and the deep brain stimulation, with the former being a non-invasive method and the latter being invasive. Neurotech allows us to not only figure out what is going on in the brain, but actually try to attempt to alter it. Now, neurotech has a well-established role in the medical field, where most of the groundbreaking research and practical applications have mainly been developed. Deep brain stimulation, as mentioned earlier, is able to be used in the treatment of Parkinson's and OCD by sending electrical impulses to targeted brain regions. The advanced brain-controlled prosthetics allow amputees to control artificial limbs through their thoughts. The advancements in medical neurotech underscore how precise and effective existing methods have become. This also sets the stage for broader applications beyond the clinical environment. Now you might be wondering, why should we, as software engineers, care about neurotech? The answer is simple. Neurotech introduces a completely new way of interacting with computers, one that goes beyond the traditional inputs such as keyboards, mice, and touchscreens. Imagine being able to control your computer or a software application directly with your mind. With brain-computer interfaces, this isn't science fiction anymore. It's already being explored in various forms today. Neurotech has the potential to enhance accessibility for users with disabilities, enable more immersive gaming and virtual reality experiences, and even create user interfaces that respond in real time to our mental states. OpenBCI is one such company making use of brain-computer interfaces. In their demonstration in 2023, they showed the capabilities of their BCI system. Christian Balin, who suffers from severe muscular dystrophy, was able to fly a drone using a VI headset equipped with OpenBCI's technology. The technology used an EEG that detected the brainwaves and used the BCI to interact with the drone. Neuralink, which many of you probably have heard about, is attempting to create an invasive BCI by implanting the chips directly into a person's head. This would create a seamless brain-computer interface and allow for more reliable brainwave data to be captured and used. But Ron, what does any of this have to do with bending a spoon? I'd like to show you a video that sparked this topic for me in the first place. Voila, bending a spoon with your mind. Well, technically it's a fork, but you get the point. If it wasn't clear what was happening, there's an EEG that, when the man focuses intently, causes a servo motor to be activated, pulling the spoon back. Okay, cool, now what? Well, one of the key takeaways I had from that video, though, was that there's now commercially available EEGs that one can simply purchase and do stuff with. Those fancy things you expected to see only in hospitals or YouTube videos is now easily accessible to a consumer. This project demonstrates that even with off-the-shelf EEGs, we can create interactive, mind-controlled applications. But is bending a spoon really the best that one can do with this technology? Well, perhaps consider playing a video game with your mind. Perry Carial is a Twitch streamer who is known for using B-side technology to play video games. This is definitely a big step up from using an EEG to bend a spoon, but the concept stays the same. She uses an EEG to measure her brainwaves, which is then used to determine inputs into a game. And to be clear, I'm not talking about games like Tetris or Minesweeper. I'd like to show you a video of her. This is a video of her playing Elden Ring, which, for those unfamiliar, is a game known for being quite hard to play regularly, which makes this all the more impressive. So how did she do this? Well, as she has explained, she used an emotive Epoch X EEG that she purchased, along with the provided API and software to measure her brainwaves. The image here shows a brain activity visualizer that was included in the software. Four distinct thoughts were chosen based on the brainwave patterns they then produced. Using a machine learning algorithm, she trained her system to determine when those four distinct brainwaves were detected. By mapping the brainwave patterns to different keys, she was able to perform different actions in the game. Of course, a game requires more than 4 keys to play. So for movement and aiming, she used an eye tracker and head tilt measuring system. However, sprinting, dodging, attacking, and healing were controlled purely by her brain. What is interesting to note, though, is that it's not yet as simple as imagining just sprinting or dodging. As she has explained, there had to be quite distinct thoughts, even involving brain activity linked to different senses. So, for sprinting, she imagines herself pushing a cube. For dodging, she imagines herself spinning a plate to "You spin me around" by Dead or Alive. For attacking, she imagines a little cricket hopping and also pulses her inner ear muscles. And finally, for healing, she imagines getting super tense, hot, and angry. These four thoughts involve different parts of the brain and create four distinct brainwave patterns, enabling different actions to be done. There exist many cool projects that make use of neurotech, and it's becoming increasingly easier to develop these, whether it be playing a video game, creating music using the brain, or enabling interactive immersive VR experiences. It is evident that these technologies are not out of our reach anymore, and just might be worth giving a shot yourself. Thank you. Any questions?
Okay, I'm gonna open up the floor to some questions. Any questions in the room? Going once, going twice. Okay.
Right. Hi.
Hello.
I'm just wondering about the delay between like someone's thoughts and triggering an action. With the current stuff that's available today, would you say that that's still like kind of a bottleneck that people have to deal with, or is it like pretty much real time, thought to action?
I think right now, compared to what it was probably like 5-10 years ago, is significantly faster, as you're able to see that she was able to play an actual real-time game. That's why I mentioned she's not just. Hello, sorry about that. As I mentioned, like she's not just playing games like Tetris or Minesweeper, so it is possible to a degree. Probably more intensive things such as driving a car with your mind is probably not accessible just yet. But yeah.
Anything else from the floor? Okay, all the way back.
With the EEG system diagram that you showed there, do you know if increasing the number of electrodes increases the performance, or if you only need those key electrodes on the EEG to do that? Because I assume you're using the basic 12 electrode system, because I know you can put that from 12 to 25, I think. Does that increase the performance there?
So definitely probably does increase the resolution. I assume it would also decrease the speed, however. The diagram I showed was based on what's commercially available. And I think those tend to stay on the lower amounts. You can probably spend significant more amount of money to get better resolution EEG. Yeah.
Okay, cool. Thanks.
Cool. Thanks for the questions, guys. Anything else from the floor or online? Nothing online, nothing on the floor. Going once, going twice, going thrice. Thank you, Ron.
Thank you.
Thank you to our speakers for today. Thank you guys for attending, and we'll see you next week. Thank you.